Okay, hello everyone, and welcome for this webinar. So today we are going to talk about OMI. So what is OMI? OMI is our automated OrganChip platform that we have developed at Fluigent. And the idea of this webinar is that we are going to present you how does OMI work, how you can use it for your application and your experiment. I think we have everyone here. So maybe we will start. First of all, I will maybe introduce myself. My name is Adam Mesian. I'm working as project manager at Fluigent, and I was responsible and in charge of the development in the marketing team of the project OMI. And today I'm with William. So maybe I will let you introduce yourself, William.
Yes, so I am William Cesar. I've been managing the development of this product since the beginning, a few years ago, and now we are very proud to release it and present it to you today.
Okay, perfect. So let's start now. A bit of an overview of this presentation. First of all, I know that you are all aware about what is OrganChip, but I will briefly introduce OrganChip for those who are not aware about these technologies. We are going to understand the limitation in OrganChip, the challenges, and also introduce OMI, what is OMI and how OMI can answer some of the challenges. Then we will see OMI in details. What are the capabilities of this product? What are the technical description? How does it work? And then the third part will be about how to control OMI, how you can use it. You will see that there is different way of using OMI. You can use it manually, you can use it with different with an application that we have developed. And then at the end, I will propose you to have a nice interaction together. So we will have a small demonstration where we will present you as much as we can the project. You will be able to see how we can open the OMI, how we can use every component. And in the meantime, you will be able to ask directly your questions. So why OrganChip? Basically, what is OrganChip? So OrganChip is a technology that allows to recreate and simulate physiological behavior of an organ. So the idea is to using a microfluidic chip, culture cells in 2D, 3D with different channels, and to apply different physiological relevant behavior, such as the fluid flow that can happen in our body. Also mechanical stretch for certain organ, for example, the heart, the lung, and it's something that is possible. And the idea is to reproduce all of this behavior and let's say 3D function inside the small microfluidic chip where we'll have the cells in culture. Why OrganChip is a huge technology and is becoming really widespread? It's because for drug testing and drug discovery, actually, currently, there is widespread techniques which are, for example, 2D cell culture, 2D cell culture that are widely used, but however they are lacking some physiological relevance and complexity. They are highly reproducible, however, they do not reproduce the whole environment of the cells inside the body. Then there is 3D cell culture. 3D cell culture could be a bit more relevant because you have the extracellular matrix in the matrix, so you have the cells which are in the 3D environment. However, you are still in static, so you do not have the flow of the liquid. Then more, let's say, relevant are animal testing, so they are better. In terms of relevance, they have higher complexity. However, they are far from the behavior of the human organ in the human body, and also they are also raising some ethical issue. So the idea was to try to combine all these techniques and try to have the same relevance, even better relevance in terms of physiology, and also higher reproducibility, and to overcome the limitation of the current technology to have a technology that allows to test drugs in the let's say the most close environment than the body. So this is why OrganChip has a huge added value. It allows to develop preclinical models used in biomedical. It simulates the in vivo physiology by flowing, for example, blood flow, stretching the membrane, as I said, and it allows many tests in terms of drug discovery and drug testing. It can also revolution the drug development pipeline. I don't know if you are aware, but the Food and Drug Administration Association, which are responsible of all the, let's say, the normative around the new drugs on the market, they have allowed last year to use other technology than 3D cell culture or animal models to test the drug for clinical trial. And so this is the, let's say, new improvement in terms of this for this technology. And this is where we are going. So the OrganChip is going more widespread in research. And of course, it's bridging the gap between animal studies and clinical trials involving human subjects. It also allows new technology, automation, long-term liquid handling, recirculation, adding sensor on microfluidic chips to analyze the oxygen level on the fluid, the glycemia on some fluid as well. So it allows many application and many automation as well. So one important step for OrganChip is to have something which allows to get all benefits of this OrganChip technology, to automate every steps, to have a really precise fluid handling solution. And so at Fluigent, we are responsible about that. Our expertise of area is on the liquid handling solution. And we have noticed that with the increasing interest of the OrganChip, there is clearly a need for fluid handling system that allows to perform different things. So first, we have seen that precise control of the flow rate and the shear stress were necessary for this application to have reproducible results. One important parameter is that when you are working in your experiment, you are working under the hood, you are going into the incubator, you let incubate for a long term. Then after that, you want to image your sample under the microscope. So there is a need for a portable, compact, let's say, fluid handling system that allows you to move your system while it's still running from an area to another. Also, fluid handling system that can be compatible with any kind of microfluidic chips, any model that you already developed, homemade model made of PGMs, for example, but also commercially available models to be able to be compatible to your current research field. Also, added value would be to have something that can be monitored from different places, to not need to be in front of the experiment all the time, in the lab all the time, to check that the experiment is running well. And the last but not least is to have a long-term recirculation. I would like to maybe go in detail into this thing. Why long-term recirculation? Why liquid recirculation in vitro for cells? First of all, it's really important to have a recirculation of the media for the cells, because the cells, we want to be as close as possible as what is happening into our body. And the cells in the body are always under shear stress and flow. There is liquid flowing all the time. So we want to be in a good condition to have the best and more reproducible results. The idea is to provide fresh supply of nutrients and oxygen to the cells. Also, you know that when you are making an experiment, a long-term culture, the cells are secreting factors all the time. And these factors are helping are part of the development of the cells. And testing a drug, for example, on cells that are not secreting on the media that do not have any secretion will lead to different results. So the idea is to have a recirculation. Recirculation is really important to keep this secreted factor inside the media that is recirculating during all the experiments. And also it allows to have long-term experiments for cell lines. It could be hours, but sometimes you can have let's say, the need to make long-term experiments from days to weeks to have better results. So there is different technology that allows to make that kind of fluid recirculation, such as gravity-driven flow. So the rocking plate that you all know, it's something which is easy to set up, easy to scale up, because you can have a lot of wells, same experiments. However, you do not have any control of the flow rate. This is not unidirectional, so that's changing the shear stress all the time, and that are not allowed to make long-term experiments. There is peristaltic pump, widely used as well, easy to set up, that allows to flow a large volume. However, they have low reproducibility because they are pulsative flow. They do not have a precise control of the flow rate and on the shear stress. And the last one is the syringe pump, which is quite easy to set up. However, you have, let's say, low control on the flow rate. As you are using mechanical action, you have pulsatil flow as well. You cannot use large volume. You are limited to syringe. It's difficult to make long-term experiments. So that's why, that's why we have launched OMI into the organ-on-chip field. So this is our contribution to this new field. This is OMI. So what is OMI? Basically, OMI is a versatile and automated organ-on-chip platform that allows to make different type of applications for in vitro testing, drug efficiency, disease modeling, and many other applications. The idea is that we wanted to get rid of the, let's say, microphysics aspect, which can be hard to handle. We know that you are working on biology, you are a researcher in this field, you want to use microphysics as a tool. So the idea was to really simplify the use of microphysics and to, let's say, at the end, not see the microphysics behind. We are taking care of it, and you are focusing on your experiments. OMI can allows you to define your own protocol. You can prepare your recirculation for weeks, then want to have a sampling at the end of the recirculation. You want to inject drug. You want to make different type of application. You can make your own protocol, launch it on OMI, and generate a long-term experiment. You can perform long-term cell culture under precise and stable flow. So this will lead to a high ideal shear stress condition. OMI, as you will see, is really compact and portable. It can fit for microscopy imaging under a microscope. It can be positioned under it's compatible with incubator as well. So you can put it inside incubator. And it also have the ability to, let's say, have a remote control through Wi-Fi connectivity. And you can check your data from, let's say, anywhere if you have Wi-Fi access. So now we will go in details about OMI, how does it work, and also the description of the project. So we'll let you, William, present this part.
So I will start with just the basic capabilities of OMI. So when you look at OMI, the first thing you can notice is that there are 4 features here that are actually reservoirs. So when you look at the fluidic configuration, you can depict the fluidic layout as follows. So you have those 4 reservoirs. The 2 on the left are dedicated for injecting fluids. So that is why they are called I. There is RI and I at the left. And on the right, those reservoirs are dedicated to as an output reservoirs. So one is called RO and one is called O. Why is there R? It is because you can recirculate between the 2 R reservoirs. So R like recirculation. So a first thing you can do is to perfuse. What you call perfusion is injecting from RI to the chip, and then it's collected to RO. The second function is, as I said, recirculation. So you can first inject from RI to RO, and then you have a refill step that injects back what has been perfused through the chip into array, and you have you change cycles so that you can basically do this as long as you want, and you perform a unidirectional recirculation in the chip. You have an injection function, so you can inject from the I reservoir to the chip and collect it to arrow. So if you want, for example, to perfuse a drug and collect it in arrow, you can do this through this reservoir, and a sampling function in which you collect what has been recirculated before into the reservoir, or that is dedicated to collecting, sampling what has been perfused in the chip. Okay, so there is a video that explains you how to manipulate the liquid. So here you see you are injecting in arrow, you are preparing your sample. So the first step would be to prepare everything into the hood. And when it's ready, you can basically put it in the incubator to perform the cell culture itself. And then when you need to observe what's going on in the chip, you can remove it from the incubator and place it under the microscope. So as OMI is totally autonomous, you can unplug it and transport it from one element to another freely. There is a battery inside, so it will still keep working while you're moving the device from the hood to the incubator or the microscope. So it's also an autonomous device, and you can automate your protocols. So there is an Android application that you can use. And with this application, you can define protocols that are basically a list of actions. Those actions are, for example, the one I just told before. So injection, for example, sampling, perfusion, or recirculation. So how it works, you just drag and drop those functions, and it makes a sequence. So you program it on your tablet, and then you load it to OMI. And when the program has been loaded into OMI, you can launch it, and it will be totally autonomous. Still on the tablet, when it will be running, you can connect it through Bluetooth or Wi-Fi, and you will see what's going on your device. So here, for example, you are monitoring your running OMI during a recirculation step, and you can see different parameters such as the pressure. What is the pressure in your OMI? So yeah, and also in terms of chip compatibility, OMI is totally versatile. So you can connect any chip that has one input and one output, and it will recirculate through this channel. There are two ways you can use your OMI. So one is standalone. So if you have a chip with just one inlet, one outlet, and one channel, you can perfuse through this one channel, but you can also couple two OMIs together, so they will be totally synchronized. And for application, for example, that has two different organs, you can flow those two channels that belong to the same chip, but with two OMIs. So basically, one OMI deals with one channel, but if you have one chip with two channels, you can couple two OMI so that they will perfuse the two channels together. Also, OMI has been thought to be compact in a way that you can put several of them into one incubator plate, and you can monitor it with the application up to 12 OMI connected at the same time. So if you really want to duplicate your application, you can do it up to 12 times using one tablet. So now more in detail on OMI's features. So when it's closed, you can see here you have a screen. Actually, it's a touch screen, so it will display what is the status of the OMI, and you can also do some manual operation that will be described later on. You have the reservoirs that you can still access when it is closed. It is closed using magnetic locks, and you can have a chip holders for standard microscope plate formats, but if you want to use your own format for your chip, you can still connect it using your own chip holder if you want. And when you open it, you can see that actually the reservoirs belong to a cartridge that is removable actually. And you have this element here that is an adapter. So it will make the connection between your chip and the reservoirs. About those fluidic elements, so the cartridge is delivered sterile, and it is considered as a disposable, so you can use for one experiment and then dispose of it. And the adapter, so why do we need an adapter? Actually, it depends on the design of your chip. If your chip is not resistive at all, you can use an adapter that has a very long microchannel in it. It will make a high resistance, so the control of the flow control basically will be better using this adapter. On the contrary, if your chip is very resistive, you don't need to add extra resistance, so you have an adapter that is low resistive that you can use instead. So now I'll give you maybe more technical details, so you don't necessarily need to know this, but maybe for your understanding of the machine, we'll just describe a bit more in detail how it works. So here you see a cross view of the cartridge with the 4 reservoirs. And you can see that, well, if you put the caps at the bottom, you have access to put pressure basically. So how the flow is driven through pressure. You can set a pressure at the top of the liquid in the reservoir. That is why also it's really important to tight correctly the caps. And depending on the pressure difference between the input and output reservoirs, you can set the flow the way you want. So there are actually other features in the cartridge. Those are embedded check valves that allows, that prevents the flow to get back in the reservoirs. So depending on what is the pressure you put in on each reservoir, it will allow the liquid, for example, to be injected from RI reservoir to O or RO, or depending on the pressure. A bit more complicated. The diagram here shows the global structure of the layout. So it's a patented layout. So it's we have it's a new technology that we propose here. So you have in the machine a manifold on which you embed some valves that control whether the pressure from the integrated pump is set in the reservoir or not. You also have level sensors that are placed just close to the reservoir to detect if the liquid has reached the top limit of the reservoir or the reservoir is empty. By knowing this level state, you can actually automate and secure your experiments. For example, if you detect that an input reservoir is close to be empty, you will stop the experiment, otherwise you will inject air in your chip and it will destroy your experiment, so you don't want that. Well, basically, if you have more questions on this thing, maybe you can ask them in the Q&A panel. I can describe it more if you need it. And just a few details on the fluidic elements. So here you see a cartridge that has been removed from the machine. They are made of polycarbonates, so they are compatible with cleaning solution based on ethanol, for example. The check valve inside are medical grade silicone, so it's totally biocompatible. And also it has a magnet so that when you insert the element in the machine, you can detect whether it's here or not. So it means that the machine is actually totally secured and you cannot run an experiment if you detect that there is a missing element. It's a bit similar for the adapter. So you have two versions, as I said, the one which is low resistive and one which is high resistive with a channel of 2 meters in it. And it is also in polycarbonate. You can use very standard connectors, fittings to connect your chip using also standard tubing, such as 1/16 of inch outer diameter tubing, but also other kind of exotic tubing. I mean, this is quite standard. So whatever the type of connection you have on your chip, I'm sure we can manage connecting it. So now on how to control OMI. So the first simplest way to control OMI is to use the touch screen. Here you can see when you will enter the menu here in the burger menu, you will be proposed, let's say an information menu where you can get access to some technical information of the machine, but more importantly, you have access to the manual mode. So through this mode, you can select from which reservoir you want to inject, from which reservoir would be the output reservoir. So here it is Ri and the output reservoir is O. And you can set a flow rate and just run a perfusion. You can also, if you want, select recirculation and it will recirculate. So this is really easy when you want to do some quick test or quick first operation before launching a real protocol. So yes, it's quite for convenience that this mode exists. Just by the way, here you can see that you have a shear stress that is indicated here. So the machine also, you can deliver flow rates, but if you give some information on your chip geometry, so for the standard geometries that are circular channel and rectangular channel, you can also have an indication of the shear stress directly, which sometimes is more important depending on your application. So in this mode, you don't need any Bluetooth or Wi-Fi. You can just control directly. A more advanced way to control your tablet, as I explained, is to use your OMI is to use a tablet through the OMI application. So when you run it, the first time you have to create an account. It will basically be registered on the cloud. It will also, as we will explain, create an account on the web application. And then you can pair the different OMI that you have, and it will display all the OMI. So for example, here, you have two OMI that are connected to your tablet, in this case, the status. So here, for the example, when it's in red, it's basically in error. For example, if you don't have any cartridge, it will be red because you cannot run any experiments in this case. So, well, you basically see the status of each OMI, and if you click on one OMI, then you will have more specific information on this specific OMI. And also, there is a web interface that we call OMI Web. You can access from anywhere, basically from your office, to see what's happening in your running experiments. Also, you can check what the past experiments, and you have a lot of options there that you can access. For example, if you want to basically send feedback to us, it is possible to do through this interface. And here for the example, you can see that you have an experiment that has had a recirculation where you see the different cycles of perfusing and refilling. So just some more information on recirculation. Here you can see two cycles of recirculation. In orange, you have the flow rate, which here it is set as 5 microliter per minute. And in purple, it is the pressure. So you can see that when you finish your first cycle, well, it will here push at 40 millibar. And here, basically, either the input reservoir has been detected empty, so you don't want to inject air, so you will switch to refill, or the output reservoir is detected full, so in both cases, you want to launch a refill. So it stops pressurizing, the flow drops, but just for a few moments, and the pressure increases to transfer the liquid from the output reservoir to the input reservoir, and then you will start a new cycle of perfusion. And last but not least, it maybe look a bit complicated, but this is basically how the connection works between all the different devices. So when your OMI is able to communicate to the tablet through Bluetooth or Wi-Fi, the only thing that you need for sure is a Wi-Fi connection when you start connecting the application. You need a Wi-Fi connection to log in the application, and then you can fully edit the protocols and transfer it to the Wi-Fi, the OMI, through either Bluetooth or Wi-Fi. When OMI is running, it is autonomous, but it still can communicate to the tablet through Wi-Fi or Bluetooth. And in any case, OMI speaks to the cloud to transfer data. And if either this connection does not exist or those connection does not exist, it will the data that has been generated will be stored internally, and you can transfer it later on. And in any time, you can connect using your PC to the cloud to get the data and the status of the experiment. So now I'm done with those technical details. I think we can go on with the demonstration.
Yes. Yeah, we will go on the demonstration now. The idea is that we present you OMI with a zoom on OMI and all the components of OMI. If you already have some question, we can start answering at the same time. And if you have, the idea is that we have interactivity at that time. So if you have question, feel free to ask it now.
So there is one question on the sterility of the flow sensor. So yes, in the system, there is a flow sensor inside the machine, so you cannot remove it, indeed. The sterility is ensured through 2 steps. So when you start an experiment, you will see in the app that in the protocol, you have a specific step that is called sterilization, and where you are asked to put in the reservoir some cleaning solutions in a given order. So as a user, you just have to follow those steps, and you will clean the reservoir this way before an experiment. Also, there is another step at the end of the protocol that is cleaning. And here you ensure that everything that has gone through the reservoir, if there is some deposition of some material, you will cleaning so that in the end your application, I mean, the system will be sterile. So there is another question on the capacity of the reservoirs. And can the flow profile be defined for periods of time? So the capacity of the reservoirs are maximum 4 milliliters, and you need, the reservoir will be considered as a low level if it's around 1 milliliter of reservoir. You need a security so that you don't inject air. Yes, through the protocols, you can totally define all the timings. So either you can control in time. So if a step of infusion, perfusion or recirculation, you can control if it ends after a given time or when a given volume has been transferred, for example. You can also control the flow profile, so you can define if the shape of the flow profile is a sinus, square shape, or a triangle shape. You can go too high. You cannot go too high in frequency, because you have limitations of the system, but you can still define sinus as a flow profile. The maximum flow it can reach is 1 milliliter per minute. It can actually go a bit higher, but we don't go certify that it will be well controlled. So you can consider it can go up to 1 milliliter per minute. And the maximum pressure, it can reach 600 millibar maximum. There is no bubble trap in the system. You can add it if you want. There exist some bubble traps that you could place between OMI and your chip. But basically, there is all the security of the system has been thought to prevent air to be mistakenly injected during any steps of perfusion or recirculation. Fourth question, yes, we can program. No, can you repeat back? Sorry. You can program the flow rates totally. And finally, can the chip be programmed for pneumatic applications? So not on this version, actually. in theory, you could basically, if you don't put any liquid in your sensor, it will inject air, and you could imagine having an application where you inject air in the chip. In this version, unfortunately, it has not been implemented. Why? It's because you have a security basically that wants to prevent injecting air to prevent bubbles. So it is not compatible in this case. But depending on your need, if you have some specific need, we could implement it in a future version. There is a question on the multiple users to connect simultaneously on the same account to check data. I think it is possible. I don't have the definite answer, but I don't think there is anything that would prevent that actually.
You could, when you are creating basically an account, you are creating a team where you will see all your OMI that are running with the experiments. So if you are part of the team, you can check the experiments of every OMI that are in the team actually.
Yeah, we thought the structure of the users in a way that allows sharing data. So this is what is called a team. So different accounts can be part of the same team, can use the same OMI, and you can define if you want to share data or not with the different users.
Maybe in the meantime, before we answer all the questions, because there is a lot of questions, maybe I can show you briefly how does it work. I think you are seeing everyone are seeing well. So here is OMI. So you have OMI here is already let's say it's working actually. So you have OMI here. It's not connected as you can see in the power supply. So I can use it. So there is OMI here. Then I have my cartridge here, which is what William presented before with the 4 reservoirs, RI, RO, I, and O. You have it here. And then I have my microfluidic chip adapter. And I have a microfluidic chip, standard microfluidic chip. So the idea is that I will open my OMI here. I will position first my cartridge in this way. Then I will position my adapter. I'm closing it. And then if I want, I can connect a microfluidic chip. So the microfluidic chip. That I can position here. So this is the idea. Here I have my setup in here. So now, if I want to make an experiment, I can directly fill my reservoir by opening, as we saw in the video, the reservoir RI here. And if I want the recirculation arrow here, I will inject some fluid inside, close it really tight to make sure that I have no leakage in terms of pressure. And then here it's working. I have a tablet and I have already paired my OMI with my tablet. I will not go in all the demonstration to gain some time to answer the question, but the idea is to present you a bit. So here I have a visualization of on the tablet on the application. I have my OMI here. Just opening. So now I have it here. And here I have the protocol edition. So I can put new and create a protocol. So by dragging and dropping, for example, recirculation step, here I can put, for example, 10 microliter per minute. Then I can inject a steady flow rate. And then this is working like this. So I'm injecting some function and I'm building my protocol. When it's done, I just save my protocol and then I launch it directly to the OMI and then it's running. And after that, when I load my protocol, for example, here I load a simple perfusion. I have no liquid inside, but the reservoir will be pressurized and will inject flow rate inside the chip, and it's running like this. And I have in my tablet all the steps that are going during the sequence, and I can know each step. Where am I? If I'm reaching the flow rate, if I'm reaching the second step and the first step, and where am I in the experiment? So basically, it's working like this. When it's done, I can either, if I'm in Wi-Fi, I have all my data on my cloud, so on OMI website. Otherwise, I have it locally in OMI, and I can just save the data on an Excel file on the tablet, and then I can just make, let's say, my analysis of all the data that I have. Okay, I think that's all for the small demonstration. We still have some question. Using what type of cells did you tested with OMI? For the moment, we have worked on different type of cells. We have a beta tester who have worked on mostly, let's say, endothelial cells to create blood vessel on chip. We have people who are working on CTC or recirculation as well. And yeah, so that's what we are working, and we are still working on it with some partner on the blood vessel. Can we connect multi-fluidic circuit embedded device with single OMI? I think in parallel connection, if for same fluidic circuit in a single device, can we control that device using single OMI?
Yeah, so you could imagine having like a T where you can connect all those 4 chips to the single output outlet of OMI. The only thing is that OMI will control the total flow rate. And in theory, if the 4 chips have the same resistance, then the flow rate will split exactly in 4 identical flow rates. But in practice, in microfluidics, it's never the case. So we would not recommend doing this unless you don't have big constraints on repeatability of the flow rates. But in theory, it will work, but not in practice, to be honest. Is there a thermal control for the nutrition? So no, OMI is meant to be put in an incubator, but there is no local control. And the 3D architecture in the chip, well, actually it depends on the chip you use. We don't provide a chip itself. You can use OMI with a microscope if the chip allows observing through it. But it depends on the chip actually. Does not depend on OMI directly.
Yeah, if I can add some word, yeah. So as we presented, OMI is let's say the system that allows to perfuse, microcirculation, and to be connected to any kind of chip. At Fluigent, we are not providing the chip itself. Here, the idea was to be compatible to let's say, the majority of chips that exist on the market, and also to be compatible with homemade chip that could be done with PDMS.
So what is the range of exerted pressure in the reservoirs? Is it possible to use a fluid whose viscosity is around 10 millipascal seconds? So the maximum pressure is 600 millibar. we don't have a precise idea of what should be the viscosity. Actually, OMI is meant to be used with mostly water-based solutions. Why? It is because of the flow meter that is calibrated for those kind of solutions. So it would work with standard flow, cell culture mediums, even with some other solution in it, like fetal bovine serum, a little bit diluted, that makes it a little bit more thick, maybe, and it will still don't need to be have a flow sensor reconfiguration, but I'm not sure using too thick solution would be compatible with the sensor, the flow sensor itself. So I don't have a precise answer on this question, but I'm not really sure. On the lifetime of OMI, so we have thoroughly tested it during weeks into a humid incubator, so saturated humidity at 37 degrees. So so far we have OMI that survived for months now. We don't have maybe enough feedback to precisely answer the full lifetime. If you take the components one by one, it's definitely more than 1 year, which is the warranty of the machine. Well, in this case as well, I don't have a precise answer to this. But for what we have tested so far, it survives like several months into this harsh environment.
And maybe to also clarify something. So I don't know if we have said it really well, but the cartridge and also adapter are consumable. So we are going to provide when you are, for example, if you are buying on the platform, it contains a triplicate of the cartridge, the adapter. And the idea is that for each experiment, you are using a different cartridge and adapter.
So question from Elise. Is it compatible with autoclave? So in theory, yes. The only point is, I mean, if you take all the materials all together, it works, but we do not recommend this because it may affect the fluidic channels inside and also the valve itself. So it's more meant to be used like a consumable and maybe to be cleaned with a cleaning solution. But autoclave might be a bit harsh.
No, we do not attest that you will have the same, let's say, performances if you autoclave it and clean it. So we are proposing the cartridge as a consumable.
Is it possible to exert profile-based pressure on reservoir like a sinusoidal? So yes, it's possible, and it will affect the flow profile as well. Sinusoid, square, and triangle shape. So how many pumps does OMI incorporate? One for each reservoir? No, there is one central pump, and the pressure is addressed individually in each reservoir through one pressure selection valve associated to each reservoir. The minimum flow rate achievable, well, the sensor itself is able to measure through with the resolution of 0.1 microliter per minute. We would recommend to have a very accurate measurement, to use it like around 5 microliter per minute. You can, in theory, go beyond, I mean, under this this flow. But the the accuracy is maybe not that high in this case.
Below 5 microliter per minute, you will be able to make your experiment. However, it's just the accuracy that will change, as William said.
To understand well, if I have a chip with 2 chambers and 2 separated channels, do I need 2 different OMI platforms? So yes. Basically the philosophy of OMI is 1 OMI per channel.
So if you're making a co-culture, this is what you are thinking about, 1 channel at the top, 1 channel at the bottom, you will need to have 2 OMI synchronized. So we have different offer for 1 OMI because you only need 1 tablet with 1 application for 1 OMI, but also for 2 OMI, this is 1 tablet, where you will synchronize the 2 together. If you have 3, if you have 6, if you have all the time. So there is different offer, but yes, 1 OMI is 1 channel with recirculation, perfusion, injection, and sampling.
And finally, last question, could the O reservoir act as a pressure sensor to detect change of pressure in the chip? There is actually only 1 pressure sensor in the system, which is the sensor that is used to regulate the pressure at the output of the pump, so the pressure that set in the pressurized reservoirs. So I don't think this would be possible because it's really the only pressure that you are measuring in the system. It is the input pressure. But maybe you have something else in mind that I don't understand. So if you have more specific question, maybe we can elaborate a bit more. Where is the flow sensor integrated, after the chip or before? It is before the chip. It's at the output of the inlet reservoirs.
It's inside the OMI. Okay, so I think no more question. Thank you everyone for attending this webinar.
Thank you very much.
And have a good day. If you have specific question, either contact us at fluigent.com or contact fluigent.com. And I think there's no question. And thank you everyone and have a good day.